Integration by substitution is a powerful tool, but as we have seen, it can be difficult to recognize an integral as being in the form of a prime of u of x times u prime of x. If we are lucky, we can use algebra to rewrite an integral to set it up for a particular substitution. In the case of trigonometric integrals, this algebra involves the Pythagorean identities, which I repeated here for convenience. It will be helpful to remember these three equations. If you notice, the second identity follows from the first one by dividing by all sides by cosine square of x. If we divide all sides of the first identity by cosine square of x, we get the second identity. In the same way, the third identity follows from the first one by dividing all sides by sine square of x. Divide all sides by sine square of x. We get the third identity. With the Pythagorean identities, we can freely write even powers of the sine x, tangent x, cotangent x in terms of even powers of cosine x, secant x, and cosecant x, and vice versa. For example, using the first Pythagorean identity, sine square of x plus cosine square of x equal 1, we can write cosine the power of 4x in terms of sine in this way. Cosine square of x squared. From the first identity, we can get cosine square of x equal 1 minus sine square of x. Okay, we replace that cosine square of x by 1 minus sine square. Now, this equation in mind, consider the integral of cosine power of 5x dx. As it is written, we don't know how to solve it. But if we keep one copy of cosine x and change the rest of them to the sine x by using the Pythagorean identities in this way, cosine power of 4x cosine x dx, we keep one copy of cosine x and rewrite the rest of the cosine x in terms of sine x. 1 minus sine square of x square cosine x dx. Now, we take sine x as u. If we take sine x as u, substitution, we take du equal cosine x dx. but derivative of sine x is cosine x. So our interval comes 1 minus u squared e. Now we can raise power of 2. We'll have 1 minus 2u squared plus u power of 4 d. As you know, the integral of sum equals the sum of integrals. So we can write du minus 2 integral u squared du plus u4 du. By using the power rules, we will have u minus 2 over 3 u to the power of 3 plus 1 over 5 u to the power of 5 plus c. So if we replace u by sine x, we'll have sine x minus 2 over 3 sine cube x plus 1 over 5 sine power of 5 x plus. In general, we would like to rewrite trigonometric integrals so that they are expressed in terms of a single trigonometric function multiplied by the derivative of that trigonometric function. For example, we can use the method for some integrals of the form sine to power of mx times cosine to power of nx dx. When either m or n is odd, since that case, we can convert all but one sine or cosine into the other function and apply the substitution. So, for example, if we have sine to power of 8x cosine power of 3x dx. So here the power of cosine is odd. So we can use this and convert to the sine x. We keep one copy of cosine x and the rest of them, cosine square x, we convert to sine x. So what we get? We get sine power of 8x cosine square x cosine x dx. We keep this copy and the rest of them convert to sine x. Sine power of 8x 1 minus sine power of 2x cosine x dx. Now we take sine x as u. From here, we will have du equal cosine x dx. Now, our integrals come u to the power of a 1 minus u squared d. If we expand it, we'll have integral u8 du minus integral u10 d. By using the power rule, we will have 1 over 9 u to the power of 9 minus 1 over 11 to the power of 11 plus 6. Okay, as you see, very easy we found it. Now we replace u with sine x. 1 over 9 sine power of 9x minus 1 over 11 sine power of 11x plus c constant. Similarly, we can use this method for some integrals of the form secant to power of mx tangent to power of nx dx. If m is the even, we keep two copy of secant x, and rest of them we convert to tangent x. If n is odd, we keep one copy of secant x tangent x, and rest of the integrand we write in the terms of secant x. For example, if we have that integral secant 6x tangent 5x dx. Okay, now you can see that case we can use both cases. We can keep two secant of x, two copy of secant x, and convert secant to the power of 4x to tangent x, or we keep one copy of secant times tangent x and convert the rest of the tangent to secant x. So let's keep two copy of secant x and what we have secant square x power of 2 tangent power of 5x secant square of x dx. Now you know secant square of x by Pythagorean identity, it is equals tangent square of x plus 1 power of 2 tangent power of 5x secant square of x dx. Now we take tangent x as u. If we take tangent x u, du will be secant square of x dx. And our integrals comes u square plus 1 power of u power of 2 u to power of 5 d. Okay, if the raised power of 4 is power of 2, will be u4 plus 2u squared plus 1 times u to power of 5 du. Now we expand that, we will have u9 du plus 2u7 du plus u5 du. And if we take an integral by using power rule, we will have 1 over 10 u to power of 10 plus 1 over 4 u to power of a plus 1 over 6 u to power of 6 plus c. Now we replace u with tangent x. 1 over 10 tangent to the power of 10x plus 1 over 4 tangent to the power of 8x plus 1 over 6 tangent to the power of 6x plus c constant.